rich. So just for some definitions, San Andreas starts in Northern California, goes through kind of two main zones of famous historic big earthquakes, 1906 and 1857. That are separated from each other by what he called a 1968 kind of active area. So these are zones more complex, but notable creep. So the faults actually don't just build up strain and release it in great earthquakes, but some of the strain is accommodated aseismically. And this part of the central San Andreas is quite famous for its creeping section. So I'll show you a few examples somewhere between San Francisco down to maybe the Dragon's Back. But on the this YouTube channel, I put all these, I made this tour of just hillshades I recorded in Google Earth. So let's start up around the Bay Area. So this is a famous example. This is the 1906 earthquake surface rupture just north of San Francisco in Point Reyes. This woman's a famous botanist named Alice Eastwood, and she was friends with G.K. Gilbert, who's a famous American geologist who took this picture, and they were enjoying the surface rupture. But you want to have in your mind, this is like kind of the simplest surface rupture you can get. It's highly localized, sort of single trace, but still has this complexity of the torn turf, sort of tearing up the grass. And here it was several meters of displacement. But you almost get a sense of the pre-existing topography of this little bump right here. So there was like a little sag or saddle here that might have indicated prior activity. And here's this is not exactly the same location, but here's a hillshade along the San Andreas Fault in this area, showing that it occupies kind of the edge of this ridge. And you don't actually see great examples of strike slip offset here, but we see this sort of complex interaction between drainage that sort of flowed along the fault zone and these uplifted sort of central blocks that, maybe it's kind of, again, like a flower structure in cross section. So let's watch a little video. Let's fly from north of San Francisco. That was up where Alice Eastwood was. Here's San Francisco itself. And here, this reservoir right here is called San Andreas Reservoir. So that's why the San Andreas is named what it is. It was sort of associated with the fault zone in 1906. And so you can appreciate, hopefully, every now and then I turn off the hillshades. These are the digital terrain models. So we've filtered out the vegetation. And here we're looking at kind of a small restraining bend in the Santa Cruz Mountains, where you can still see the through-going San Andreas trace, but here it's really being affected by, well, it's hidden under the trees, but it's affected by landslides and this kind of big Stevens Creek channel that sort of incised along it. Here's some more. That area is where all those big fires have been. Now we're down here in the area of Hollister, so we're in this transition from actually it's the San Andreas Fault Zone, but that's the Calaveras Fault, and over here on the left is the Sensu Strictus San Andreas. So they're kind of bifurcating here in the southern San Francisco Bay Area. And Hollister is a place where the creep is really well manifest. So let's just look, if you go there and you visit, here's early, you can see the cars, you see this bent wall. Now time passes, the wall is deformed even more because it's 12 millimeters a year of creep localized right through these people's front yard. And so this area, then we see there's a scarp right there in town that's produced, in this case, by we think, pure creep. So, but still is building topography along the fault zone. Now we're going to move down. So the San Andreas and Calaveras kind of come together and join. And now we're back to what's officially called the San Andreas. This is a place called Dry Lake Valley that has high creep. And Chelsea just wrote a paper about it. And so one of my former students is entrenching there. But you see highly localized sort of zone along, highly localized discontinuity along the fault zone, mostly manifest by these sort of little sags. And then this feature here, it's kind of like a little shutter ridge. So it's a ridge that's sticking up that might be deflecting or shutting off some flow. Here's another deeper sag right in here. So let's keep flying along. So now, you know, we come into a part of the fault. It's still mostly creep. There's no big earthquakes here. But this is a place called Mustang Ridge where there's a very interesting distributed deformation that we'll talk about in a moment. So the Mustang Ridge is kind of a hill. And what you want to appreciate is that probably the main San Andreas is here on the side. And so you can see these discontinuous sort of little breaks in the topography. But then these features here are big extensional kind of normal faults, basically, or oblique extensional features that are developed adjacent to the fault zone. And we'll see a map of that in just a moment. So let's just, yeah, so if we go to the next slide, this is a paper written by Steve DeLong a few years ago. So again, here's the map. There's the San Andreas with some discontinuous trace, but then all these oblique slip normal faults there. And what they showed, it's a little bit hard to see, but this is a cross section. So the San Andreas actually isn't vertical here. It kind of goes dipping underneath Mustang Ridge. And so this is like this little flap of topography that's being sheared sort of by strike slip motion underneath it. And so we're sort of shredding this block. So it's very interesting. And you can get a sense of the scale here. So several kilometers in length.
So on this slide, the slide that you were just showing right there, if we were mapping the area with just this topography, right, I could see
Yep.
where I would follow these ridges and how they would connect into the faults. But I don't know if I would map those as faults. How would I recognize them as their own like faulting systems? Just from
Great question. Let's see if we go back. Never mind. I was gonna, or here. How about here? Let me just pause it because here we don't have the interpretation. So the main thing is on the side. You would say, okay, well, these are a bunch of landslides here, so they're not systematic in terms of their indication of faulting. And over here also, these drainages seem to be kind of standard, sort of typical dendritic patterns. But then when we come in here to the main zone, so, you know, I sort of get rid of things that and home in on them. But then, you know, like this right here is a scarp that is, to me, you couldn't explain it as a fluvial feature. And here's another break. So scarp just, you know, is a step in the topography, but you see that this one's cut by this drainage. So there's some kind of interaction between the drainage and these features. Here's another scarp. So again, there's no geomorphic explanation that we could use to explain like why this thing formed. So an easy example would be, well, it's a little normal fault that's sort of dropped the left side down relative to the right side. Up here is a depression that's kind of, you see it's got a flat bottom. Yeah. So it's sort of being filled probably by sediment that's coming from some of these drainages. But then, you know, that is a depression that's along this zone. And then over here, same thing. You know, and I think what you ask is a really important question, because what I was like, one time I took a colleague out to a place like this, and he was like, I don't see anything, because, you know, he was just looking at one little spot. And I was like, Vince, you can't just look at any one thing. You have to look at, you know, the ensemble, like all of these little features together suggest a fault zone. But any one of them, you know, just look at a little step, you'd be like, well, I don't know, could be fluvial. You know, same thing here. We have a bunch of strange little pieces of topography, like little ridges. So any one of them is ambiguous, but the group together suggests some kind of deformation.
Okay.
All right. So I think that's key. But what you ask is super important. And what's also really important for our class is it's likely that people would map this differently.
Mm-hmm.
And so one of the questions that we'll start to ask ourselves is what's robust? Like what does everybody get versus what are some different sort of features that people notice, or how do people sort of put it together? And so that's why I tried to give you kind of this basic language of the morpho mapping. So you have something to start with, like hopefully we all can agree on what are ridges and valleys and sharp and smooth slope breaks. But then as we start to put that interpretive layer on top, we might start to diverge in our interpretation. Right. And, again, in this case, we see the breaks in the topography, but it's even harder to find the senses of motion, like where is the exact evidence of right lateral offset? Like here, this little channel might show a little right lateral. But so much of this zone, this is mapped as the main trace, is just a trough or steps in the topography. But we might look for places where there's shutter ridges that are consistent with sort of being formed by the offset topography. It's a great question.
This is Chris. I wanted to jump in real quick. Another thing to keep in mind is it's usually not one or the other. So Ramon showed where the landslides are and where the likely faulting is. In that area of faulting, there's likely landslides as well. So you want to keep an eye out for all geomorphic features and then decide, what looks most like a fault as opposed to a landslide or another feature. So it's not always easy.
And actually what Chris, go ahead.
Huh? Oh, no, I was just agreeing. Yeah, it would be kind of difficult for me to see a lot of this stuff, but now that you've pointed out like where the scarps are and just kind of like the topography of the land, I can see it a lot more clearly now.
Well, and I think it's also, you have to be patient with yourself. You can't okay, we have experience, so we can start to pick it apart. But if you can't see anything, that's again why you have to start mapping. Just start at one end and go to the other, make yourself look at the whole thing, and then you start to see, well, what do I start to pull together? One quick comment with respect to Chris's is, one reason why Mustang Ridge looks so good is it doesn't have a whole bunch of landslides on top of it, but other parts of San Andreas nearby, northwest and southeast, have big landslides on top of them. And so in a way, I'm not showing those examples because they're sort of messier. I probably should. Rich, looks like you're about to say something.
Yeah, just one comment. So when you start studying an area like this, sometimes for me, it helps to sort of trace out some of the streams and things, or if you really see something that's a landslide, that yes, it's obviously a landslide, you might mark it with some kind of symbol on the headscarp or something like that. I mean, we're not doing quaternary geologic mapping, but some of the features, you can start eliminating them as you start to study it. And once your eye has seen that that's a stream, it helps you sort of see where fault scarps are different from that feature, and it helps you differentiate between different features just by studying it and making symbols and drawing on the map.
Exactly. So let me go for a few more minutes and then I'll turn it over, Rich. So now we're going to end up at Parkville, which is a really famous place for recurring magnitude 6 earthquakes. And that's all this is supposed to show, is that over time there has been this repeated, moderate size events. And, if you go there, it says, be here when it happens at the Parkfield Cafe. But here's a place where I went after the 2004 earthquake with one of my former students, with Nathan Tokay, and we mapped he had a trench that was open actually before the earthquake, and then we went back. And so these yellow things show the rupture pattern from the 2004 magnitude 6 Parkfield earthquake. So the point here is to sort of compare the fracture pattern with the landforms. And so what we could see is, and he's out here, this green thing is this sag right here. And so again, what we see is this simple shear zone where, it's right lateral, but there's so many of these little end echelon fractures that are associated with just that single earthquake. And so the topography that we're observing has formed by multiple earthquakes like this. And here's just a quick example of some of these fractures we surveyed, and you can kind of barely see the cracks opening. So is another key concept you have to have in your mind is we're building the topography that you're mapping incrementally and sometimes by very small increments.
He's standing on an extensional zone right there, right? So that'd be like
Yeah.
the negative flower structure.
Probably, yeah. So this is me. I'm standing like kind of probably over in here. So I'm along this zone that's sort of feeding into predominantly extensional. But I think the green patch is a little bit more where it's mostly extensional.
What are y'all measuring right in there to figure that out? Because it just looks like a field of grass to me.
Well, if you look very close, it's kind of hard to see. But what we were looking at was these cracks. Like, let's see if we can see any in here. Like, you just see these cracks in the turf.
Oh.
And so what we did when we surveyed them was we surveyed like the beginning and the end of every single crack. And if it was a long one, we surveyed some vertices along it. And then we measured the opening, like, so how much opening was there? And so that in this map shows that's the thickness of the line. So some of these cracks were open by several centimeters, whereas others were open by like half a centimeter.
Oh, cool. Thank you.
And so then just to show, this is a view from above. So there's that surface. So in terms of mapping, this is a fluvial terrace next to this popped up hill. And the fault zone kind of goes right through that terrace and has this weird sag developed on it. So again, it's kind of like the plate boundary is in this view, but it's a little bit hard to pick out if you're not sort of looking closely, right? So this is why this mapping is hard work. Just a quick final few slides. So here's Nate. He dug this huge trench on the side of that sag, and literally the material is kind of sagging into it. And so we developed this kind of a model that would explain sort of how the landscape, we have these discrete fractures, but they're breaking the ground during these little earthquakes. But over time, we sort of keep building this kind of relatively smooth landscape because we're sort of diffusing these small ground cracks away so that our eye, if we hadn't had that earthquake, we would not have really seen exactly how this whole pattern develops. So I'm going to stop there. So Rich has time and we can talk some more. I have so much more to talk about, but I want to give some balance. So any final questions? Okay, so why don't you take it away, Rich, and
Okay.
I'll stop sharing.
Okay, let me share my screen. Can everyone hear me okay? We've got a little bit of internet trouble here in California.
Sounds okay.
But,
Yes, seems fine.
Yeah. Okay.